Okay, so today, we are gonna shift gears a little bit and think about designing algorithms using sum of squares for average case problems. We kind of already shifted our attention a little bit to designing or at least considering average case problems the last time, but we didn't see any algorithm so far. And so today we are going to actually start diving into it. In fact, the next few lectures will focus exclusively on various average case problems. And so today we will begin with one example problem, which will illustrate this method of designing algorithms and how you think about them using the SOS method and so on. So in particular, we are going to focus on this problem of clustering spherical mixtures. But in general, it would be just a way for us to, study how to design algorithms for average case problems using, SOS. Good. So today, yeah, we'll focus on clustering spherical mixtures. I'll tell you what this problem is. Uh, you know, in fact, we'll essentially try to give all the details of how to design algorithm for this problem today. And yeah, as usual, I'll request, turning on your videos if you can. It doesn't, it's not mandatory, of course, but, if you can, then that will be great. Good. So, so we'll start with this. And, instead of like, so my plan, at least I was thinking how to do this right. And initially I thought I could pontificate a little bit about the general approach and then tell you about this specific application, but I thought I'll do the reverse. Okay, so we'll dive right into the details of this particular problem, and at the end, we'll basically spend a few minutes abstracting out what we learned, and trying to see a general approach for other problems using this as an example. And then we will basically implement that approach for a number of different problems in the next few lectures. So the next time, which by the way won't be November the 3rd, it would be November the 10th, we'll look at more general and interesting problems like this problem of estimating moments of distributions when there are corruptions in samples. We'll study this question of dictionary learning, uh, which happens to be roughly equivalent to this question of finding sparse vectors in subspaces. We'll study this pretty important primitive of tensor decomposition. And actually, for us, it would be equivalent to maximizing polynomials over the sphere. So, all of these things are not supposed to be understandable. They're supposed to be vaguely relatable. And the hope is that, some of these problems, at least one of these problems interests you. So, because you're going to spend quite a bit of our time on, some of these problems. We'll also look at this recent stuff on less decodable learning by means of an example. And, if there is time, then, we might look at some results about tensor completion and matrix completion, if you heard about those. But of course, there are lots of problems like this. We'll not look at every one of those in the remaining few lectures that we have, but we'll certainly, point out how the same approach that we're going to apply today is general enough to, apply to these and many other problems. Okay, good. So let's just, not talk about the generalities at all. Let's just dive right into, our today's focus, which is, this problem of clustering spherical mixtures. Okay. So, what's this problem? So, I'm going to just describe to you by describing an input. And, unlike many of our, initial classes, the inputs this time will be generated, via some, samples from a distribution. And that's the average case part of it. Okay. So that's where the average case things will come in. So our inputs will not be arbitrary. They would be generated, from some probability distribution. And in this particular case, the input is going to be, x1 up to xn. So these are like n vectors, and they're d-dimensional vectors. And how are they chosen? So I told you that, these are going to be generated from some distribution. So here's how I, imagine the process to be. So generated as follows. So, for each 1 less I less than k, I'm going to choose n over k IID samples from the following distribution. So this is the Gaussian distribution with mean vector mu sub I and identity covariance. And so this is a distribution over R to the D. So it's a distribution over D dimensional vectors. So this vector is, some arbitrary point in R to the D. Okay. So I'm going to choose n over k IID samples from this Gaussian distribution with identity covariance and mean mu sub I. And I'm going to call these points, C sub I. Okay. And I'm using this notation because, throughout today's lecture, we're going to refer to C sub i's as, true original clusters, true or original clusters. Okay. And what do? I just, take, so I have like C1, C2 up to C sub k. So, if I take the union, I'll get n points because each of them contain n over k points. So I'm just going to take the union, shuffle it, and, return. By shuffling, I just mean that, I never tell you which points were C sub I. So I'm just going to take the union and like, return them in some arbitrary order so that you can't quite read off, which points came from which CI and so on. Okay. Now, notice that mu sub i's and C sub i's both are not known to you. By you, I mean the algorithm. So, so you can call mu1 up to mu sub k. These are RD, points in RD. They're unknown to you. And you can think of them, and there's this unknown, means of these distributions. Okay, so these are not known to you. And also C1, C2, CK, the division is not known to you. Okay, so that's the input. And what's your goal? Your goal is to look at these endpoints, which I described are generated according to this probabilistic procedure. And you would like an algorithm with, let's say that, that outputs C1 hat, CK hat. Now, think of this as a partition of the input points into K buckets so that each bucket is of size n over K. Okay. And let's say for all, 1 less I less K, and there exists some permutation of the labels from 1 through K so that, C hat I intersects, C pi of I in, all but a small fraction of points. So let's say, this is 1 minus delta times n over K. Okay. And so, all this is saying is that, up to, calling the first cluster the 10th cluster or something, I have approximately recovered, these cluster structure in the points. Okay. So, in some sense, throughout this lecture, I'll keep referring to this as the original clustering of points. This was, in some sense, the natural cluster structure that the points satisfied, because that's how they were generated. Points in C sub I were generated from a different Gaussian, or at least Gaussian with a different mean. And our goal is to recover, up to these labels, basically, this C sub i's, some, up to some delta fraction errors in each cluster. Okay, that's our goal. Now, there is a related goal. So, maybe let's call it a remark. There is a related goal where, instead of just recovering the cluster structures, like instead of recovering C hat i's, you might, want to recover, good estimates of the means. And you might imagine, and you're right if you are imagining that, that, you can recover mu sub i's, or at least very good estimates of mu sub i's given C hat i's. Okay. So we will not actually focus on this particular goal today. Instead, what we will do the next time will naturally, tell you how you could have, in particular, recovered the means from the C hat eyes. But we will not focus on that goal today. We will simply focus on the goal of recovering an approximate clustering of the input data points. Okay. This can be done using C hat eyes, and I will not specify what I mean, quantitatively today. Details, let's say, in November 10 lecture. Good. So, so now I've, completely specified the problem to you. So let me pause for like 30 seconds and see if there are any issues, in the problem itself. Like, are there any questions you might have about, the setting? Okay, so no questions. uh, there should have been one question. Let's see. Are there questions in chat? Okay.
Can
Misha.
we do something?
Sorry. Yeah, go on, Pranit. Sorry.
Yeah, can we do something? Say if we are generating endpoints this way, we are choosing an I with a probability 1 over k, and then generating the point with respect to
Right.
new I.
So you're talking about the slightly different setting where you may not have exactly 1/k fraction of the points from each
Yeah.
each of the and yeah, so that's basically equivalent. This is just this simplifies notation a whole lot, and I don't have to worry about the size of the cluster and the deviation from the 1/k fraction. So that problem is
Okay.
essentially the same, but this is just simpler notation.
Oh. So what's of how does the guarantees look like in that case?
Right, yeah. So I have not specified the guarantees even in this case right now, right? But basically,
Okay.
whatever guarantees will hold in this case would also, extend to the general case where, not only when you choose I uniformly at random from 1 through k and then generate IID sample from the Gaussian with that mean, you could in fact have general weights. You could have like Gaussians appearing in different proportions, and the guarantees I'm going to talk about today actually naturally extend to the settings with general weights. But again, like just to focus on a simple setting where we can do all the details, we are going to focus on this particular world where we have exactly 1/k fraction of the points coming from each cluster.
Yeah.
Also, is my screen still visible?
Yeah.
Okay. For whatever reason, something happened on my end. Okay, maybe not. I think it's back again. Okay, very good. Right. So we'll answer some of these questions in slightly more detail that Pranit already asked. What about the natural variations of this setting that we looked at? And in general, it's always good to wonder how robust are our algorithms to various minor changes of the setting. And basically one general aspect of the algorithms of the sort that we are designing today is that they're usually very resilient to these kind of settings. Okay, and we'll make that point precise when we set the result in a second. But in terms of proving the result, we'll only focus on this specific setting, not because the other variations are harder. It's just like notation is much simpler to follow. Good. But one thing that you might be wondering is that this problem in principle should not even be soluble. um, at least if I don't specify additional conditions on mu1 up to mu sub k, right? And why is that? So let's maybe point out that issue. The problem may not be soluble as stated. Why not? Well, imagine. So I did not. I just said you have k different means. Imagine for whatever reason mu1 and mu2 are like exactly equal. Well, if mu1 and mu2 are exactly equal, there is really no difference between c1 and c2, right? Like the points in c1 and c2 look exactly the same, and so there should be no reasonable way to correctly identify which points in c1 union c2 came from c1 and which points came from c2, because in some sense there is really no distinguishing element between the two samples. And more generally, this is not just an issue of when two means are exactly equal. You might imagine that, even if means are very, very close to each other, this would be an issue. And so you might naturally imagine that the following parameter would become important. So let's call is, let's, because it's an important parameter, let's call it, whatever, let's call it separation. Should have thought of a better name, but let's just call it separation. So, I'm going to denote this quantity by delta, and delta is minimum over all pairs I and j, all distinct pairs ij of, let's say, the L2 norm of mu I minus mu j. Okay. And so what we just, discussed means that if delta is zero, we are definitely not going to be able to solve this problem. We will not be able to, find an approximately correct clustering. But in fact, you might imagine that even when delta is very, very small but non-zero, the same kind of objections will continue to stand. So there must be, some notion, some lower bound on delta for this problem to be soluble. Be some lower bound on delta to make problem soluble. And so, let's do some very heuristic reasoning to see what that, lower bound should be. Okay. So let's maybe call this part heuristic reasoning for lower bound on delta, on lower bound required lower bound on delta. Okay. And for this, let's focus on the simpler setting where, you know the means. So let's say you know mu1 up to mu sub k. So you know that, each point was somehow generated IID from one of the k possible Gaussians, and you in fact know their means, and you also know their covariances. Okay. It is still unclear, how you would cluster the points, right? Because all I've given to you are the means. I have not told you how to cluster the points. But imagine that you wanted to solve the clustering problem using your knowledge of the means. What would you do? There are various natural things you can do. I'll just, focus on one natural thing, and that will be our heuristic. The important point, of course, is that you can make this reasoning perfectly precise, and I'll state at the end the conclusion of it. But let's focus on the following simple procedure for detecting cluster structure if you know the means. So here is the simple clustering heuristic. Actually, can someone suggest what I might use here? How should I, so, I have k different clusters. I know that exactly 1 over k fraction of the points were generated from each, and they have means mu1 up to mu sub k. Now I have to decide, what each of the x1 through xn were generated from. So what should I do? What's maybe a natural thing you might try here?
Like stick points with it.
Likelihood. Oh, sorry.
So Tim says maximum likelihood. I caught that. And what did Ellis say?
I was going to say something even stupider. I was going to say just greedily stick points with the nearest cluster that has had more than n over k points.
Believe it or not, you and Tim said the same thing. Even though you said different, words, you said the same things. It turns out that the maximum likelihood, clustering given mu1 up to mu sub k, if you know what that is essentially the same as, associating xi to its nearest mean. But again, we will not discuss this. This is not a statistics/information theory class. We will just describe the heuristic. Essentially, the same heuristic that Tim and Ellis proposed is, associate each, xi to the mu j nearest to it. Okay. And again, we are not going to analyze this heuristic very formally. We're just trying to understand, when does it roughly succeed? Okay. So when will it succeed? Well, you would want that. So, let's say xi was generated from, mu sub 1. Okay, so let's say, xi, and let's say, I should have said this before, but let's say that, we are working in d equals 1. Okay, just for the purpose of this heuristic reasoning, let's assume that you're in d equals 1 so that we don't have to worry about these vectors. They're just like numbers now. So these mu1 through mu k are just points on the real line, right? And identity in one dimension just means the constant 1. So I have, a bunch of points generated from standard Gaussians with variance 1 and mean mu1 through mu k. And the clustering heuristic we tried was associate xi to the mean which is nearest to it. So now we might want to understand what's the error probability. So when do I make an error, right? Like when do I make an error in this particular way of assigning cluster labels to each point? So roughly I make an error in the following way, right? If xi was truly generated from the first Gaussian in my generation process, which nobody told us what it was, but we know it happened, right? And I make an error if for whatever reason xi happens to be nearer to some mu j, which is for j bigger than 1, right? So error if xi happens to be nearer to mu sub j for j bigger than 1, xi generated from first Gaussian So let's understand, what's the probability of that happening, right? So, it's like, let's look at, so here is mu1 on the real line, and here is, let's say, mu sub j, for some j bigger than 1. Now we're saying, xi happened to be here. Okay, and it's like slightly nearer to mu sub j than to mu sub 1. Okay, and that's why, we assigned it to mu sub j and not mu sub 1. Now, we said that mu1 through mu j, so in one dimension, the distance is simply the absolute value of mu1 minus mu j. We said that, this is bigger than delta. Okay, so let's say, this distance is exactly delta, right? In that case, I assign xi to mu sub j if, xi minus mu j happens to be, or xi minus mu1 happens to be bigger than delta by 2, right? That's the only situation when I would be nearer to mu sub j than mu sub 1. So what's the probability of that happening? So if you remember your Gaussian PDFs, then the probability of that happening should be roughly proportional to 1 over root 2 pi, whatever, there's a fixed constant, minus so if you remember the Gaussian density, it's half of the distance between the mean squared, right? So it's delta squared over 4. And now this particular calculation somehow needs to be done for each of the k clusters. So if I wanted that I don't associate with any of the k possible confusing clusters, confusing means, then I would want that k, or what really k minus 1, but doesn't matter, times this error probability is tiny, because there were like k minus 1 different clusters which could have really caused the confusion. And so we would want this to be much less than delta if I wanted to recover a 1 minus delta accurate clustering. And so now if you solve that, then it means that delta should be bigger than some constant times square root log k. Okay, so this simple associate the mean to the nearest associate a point to the nearest mean heuristic will work if the minimum pairwise distance between any pair of means is at least some big constant times square root log k, right? So far so good. And so actually
I have a question.
Yes.
Why do you need the factor of k there?
So let's understand, right? Like I am choosing. So maybe the way to so maybe maybe the right way to do this calculation is look at a point generated from a cluster which is not mu sub 1. And what's the chance that it happens to be, let's say, delta by 2 close to mu sub 1, right? Then there are k different clusters, each contribute some fraction of points, and I would like the sum of those things to be smaller than delta. So okay, let's maybe.
But like if like xi comes from actually from cluster 1,
right,
then xi is assigned to the wrong cluster only. Like if xi is assigned to the wrong cluster, then it means that like xi minus mu1 has to be at least delta over 2.
Yes.
regardless of which cluster it's assigned to.
There are two kinds of errors, right? Like the two kinds of errors are that the points in, the point generated from mu sub 1 were not assigned to mu sub 1, and that points generated from some other mu sub j were assigned to mu sub 1.
Oh, is this because you want the final clusters to all have exactly n over k points?
That again does not matter, but yeah, let's say that I want exactly 1 over k points.
Because if you didn't do that, you could just assign to the closest cluster and kind of.
No, you will still make an error in some other cluster. So that particular thing is not so much of a relaxation. But the point I'm making is very simple. I'm saying that, if I look at points generated from any one of the clusters, any one of the, any one but the first cluster, then the chance that one of the points, from that cluster is assigned to the first, cluster is, e to the minus delta squared over 8 or whatever. And now, I have k minus 1 such different clusters. So I would like.
I think, okay, no, so I'm doing the argument. I think Misha also has the same
Yeah,
question.
why can't you do it like per point?
Yeah, that's what I was saying to do. Like,
yeah,
Okay. What's the per point argument?
like per point, what's the probability of classifying it wrong? That would be only if you deviate from mu I.
Okay.
And so that is only e to the minus delta square.
Okay, perfect. So let's do it that way. So how many points I have to do, and so what's the number of points I'll make an error on? It's n times, like in expectation, the number of points I make an error on is n times e to the minus delta squared over 8, correct? Okay, so as a fraction of the cluster, what is that number? It's k times n over k. So I'll write it down. So if you do this per point argument, then yeah, so let's see, right? So total number of points, in cluster 1 that are badly assigned is, n times, e to the minus delta squared over 8 up to some constants, correct? And what am I comparing this to? I'm trying to understand what fraction of the points in C sub 1 were badly assigned, right? So as a fraction of points in C sub 1, this is k times e to the minus delta squared over 8 over root 2 pi fraction. Because C sub 1 has, only n over k points. Does that satisfy this version of the argument too? So we would like this number to be smaller than delta. And so that happens when delta capital, we would like this number to be smaller than small delta. That happens only when capital delta is bigger than some constant times square root log k. Feel free to stop me. This part should be clear. I'll tell you when, I'm okay with things being unclear, but this one I would like to be clear. All good? Misha, did I satisfy you?
Yeah, I thought for some reason that delta was the classification error per point, not per cluster, basically. Like,
right, yeah. So
like
let's look at
that was the k. That's where the factor k came in. Yeah.
Right, yeah. Yeah, good. All right, very good. So we all kind of agree that this heuristic of C root log k is reasonable, right? And actually this heuristic turns out to be essentially right, not just in 1D, but also in high D. So this heuristic calculation happens to be right. And I'll explain what that means in a second. But even before going there, let's understand what happens when, let's see what happens first when, capital delta is much bigger than, some C root log k. Okay. In that case, what's happening is we are still in 1D, right? So, we have mu1, mu2, whatever, mu3, and so on. And the pairwise distance between, any pair is at least delta, right? So, and now, now what we have arranged for in some sense is that all the points which are generated from the first cluster are like all but like a delta fraction of the points are actually close to mu sub 1 than to any other mean, right? Which means that, if I look at, the empirical distribution of points from the cluster 1, they look like this. And then if I look at the empirical distribution of the points from cluster 2, it looks like this. Similarly for, cluster 3 and so on, right? In other words, there is, if I look at, if I plot these points on a line, they'll look like this. There'll be like some red points like this. And, I'm basically, let's say, drawing, the points. I'm trying to draw the interval where, let's say, 99% of the points from first cluster are present. So it would look like this point, this interval, and then there would be some other interval for the second cluster, and, maybe interval for the third cluster. The point is that these intervals are basically completely disjoint. It doesn't mean that there are no points outside this intervals, but it means that 99% of the points from the first cluster appear in this interval, 99% of the points from the second cluster appear in a completely disjoint interval, and so on, right? In particular, if you wanted to solve the 1D problem, you don't have to do anything. You can simply, look at the points and just like manually cluster them. Okay, like for example, you could do the following simple clustering algorithm. Choose a random point and, take the n over k points which are nearest to it and call that the first cluster. And now, remove these points and repeat. So with high probability, you will succeed in this algorithm. So I just want to point out that this 1D setting is not hard at all. Even though we are going to focus a whole lot on solving it today using a more complicated algorithm, this setting is not at all hard, okay? So in particular, a simple algorithm actually works for this problem. Choose a random point. Take n over k points nearest to it. Well, maybe 1 minus 1 points nearest to it. And call it cluster 1. And just repeat. Repeat on the remaining points. And the rough reason why this simple, greedy clustering would work is because, with some large enough probability, you will always choose a point which is like, roughly near the center of these intervals. You will not, pick up things which are on the fringe. And so each time you pick up points which are like near the center, you basically are going to be reasonable in this process. Again, I don't want to analyze this algorithm because this is not our main goal, but just want to point out that, we are in a setting where, at least in 1D, things are far, the means are far apart enough that, something simple and dumb like this would work. Okay, again, feel free to stop me if there are any questions, but, hopefully, this is clear. Like in some sense, the distributions, if you look at like, where the points fall, the distributions are essentially disjoint. The overlap between, let's say 99% intervals for them is, essentially nothing, which means that, some greedy process like this would succeed. Okay, again, I'll take a 30-second pause so that things are clear and before moving on. Good. So, what have we seen? When delta is much bigger than root log k, we kind of succeed via greedy heuristic. And, at least this specific, link yourself to the nearest mean heuristic fails. If, should fail if, capital delta was much smaller than, root log k. That's rough discussion. The summary of our discussion right now is hopefully, these two observations, which are, believable to you, even if not like perfectly provable, because I did not really prove them. Okay. So now I can clarify my comment about why this heuristic is in fact giving you the right answer. So for whatever reason, this result was formally proven only in 2017, even though, the heuristic argument, what I gave you essentially predicts it. So here is what, Regev and Vijay Raghavan proved. So this is, let's say, a theorem, but I'm only going to state it informally because, again, that's not our main interest today. If delta is less than C root log K for some small enough constant K, a constant C, then there is a mixture. So the the model for generating the data that I told you is called a mixture of K Gaussian model. I didn't define this name, but I'm just going to use it because it's roughly intuitive to you, I hope. So there is a mixture of K Gaussians that needs some K to the poly C samples. Actually, maybe I can be more explicit. It's like K to the C over 1 over 24 is what they prove samples. So, like this lower bound. So just to make sure, what kind of a lower bound this is not a lower bound on running time of an algorithm. It's just saying that, if you wanted to do this right, if you wanted to do the clustering right, then you will need a large number of samples. Because you need a large number of samples, certainly you need that much amount of time because you have to read the samples. So this is an information theoretic lower bound. There is nothing, computational about it. This is just saying that, small amount of data just doesn't have enough information, for you to be able to even do this task. Okay, then are required. I already said that. While in fact they also proved the converse in a certain sense. They proved that when delta is bigger than some capital C root log K for some large enough constant, then there is a brute force algorithm. So this was not an efficient algorithm. It runs in time. I don't actually know if they even proved this, but it certainly takes d to the omega K time. Algorithm that solves the problem. So basically even though we did the heuristic reasoning only in one dimension, what Regev and Vijay Raghavan established is that even in high dimension, up to constants, the right threshold is simply square root of log K. Okay, in terms of the separation where this problem becomes even information theoretically possible. So this is only about brute force algorithms. It's not about solving the problem efficiently using algorithms, but it's at least like they give us an indication when can we even expect an algorithm to exist here. Okay, so now we can ask for algorithms which are more efficient. So in particular we want to beat this d to the omega K here, and we'll be happiest with polynomial in both d and K time algorithms. We'll see that we won't be able to get that, but we'll be able to get something reasonable. So, but before that, I guess I need to tell you, I won't go into too much of the history. It's not that instructive. I'll just tell you that, there are like a large number of works that try to solve this problem. For whatever reason, it's very interesting to both statisticians and, computer scientists. And so, there were a number of, papers that were trying to, solve this problem with smaller and smaller delta. And there was a long sequence of works in this line that culminated in this paper of Santosh Vempala and Wang from 2002, which shows that, if this capital delta is much bigger than K to the 1/4, I think the paper requires logarithmic factors in the dimension, but let's not worry too much about them. Then there is a polynomial time algorithm. And so, if you notice, this is, exponentially bigger than the square root log K threshold that we, found was somehow the right point at which, we should be able to, I should have pointed out, so the problem with, polynomial many samples. Okay, so even though we know that there is some atrocious running time, but polynomial in D and K sample algorithm that works when delta is much bigger than constant times root log K. This result says that if you're bigger than like something much bigger than root log K, like K to the 1/4, then in fact there is a polynomial time algorithm. And what we are going to, so this was of course not using sum of squares, but what we're going to see today is like an upgrade of this theorem that was proven in 2018. So today we will prove the following theorem. I'll talk about the attributions, etc. in a bit. But this theorem says that, there is a sum of squares based algorithm. So fix some number t that runs in time d to the o of t squared. For the problem, for the clustering problem. Good. Such that with probability at least 1 minus 1 over d, it outputs, whatever the good c hat k's, satisfying that are delta approximate clustering for some delta which is smaller than capital delta to the minus 2t. We'll interpret this expression in a second, but I'll just write it down first. So this statement is telling you something that's true for true in terms of every possible value of this capital delta separation, but you'll see that it's actually not even meaningful when delta is smaller than root log k. Even though the expression is written down here, it won't make sense when delta is too small. So to understand this statement, let's understand this statement. It's to understand this statement, let's set our goal to be getting a 99% accurate clustering. So we can only make a 1% error in each cluster. Okay, let's say that's our goal. And let's try to understand what does this algorithm say in that particular setting. Okay, so if I want delta to be 0.01, then I have to force. So I'm just going to write down this expression I wrote down above. Sorry. Delta square to the t. So I have to somehow ensure that this is smaller than 0.01, right? So first, let's choose delta to be some large constant. I think I checked that this works, but we'll see. 10,000 root log k. Okay, so for this, I want to claim that t, which is log k, would work. Sorry, t, which is square root log k, would work. No, I take it back. I want to say t equals log k. Final one. So let's see why I think that's true. So the point is, if I square delta, then the log k cancels out the inside expression over here. The log k's cancel out, and you get like some constant. So let's write down that constant. I think it is 10 to the 8. Seems like maybe 100 would have worked here. Maybe 10 to the 4 is not needed. So the expression, above is at most, some number, less than 1,000 over 10 to the 8 to the log k, and you can imagine times k cubed. And all I need is that this is like some very small number. So it's, let's see, it's like 10 to the minus 7 log k times k cubed. So you can imagine that this. If I got my math right, then this is much less than 0.01. Okay, so what have I done? I've told you that if I choose delta equals some big constant times root log k, I think 100 would have worked. By the way, here I think I chose too large a constant, and so if I choose delta equals, let's say 100 root log k and t equals log k, then I have a valid setting of parameters. So this means that when delta is some constant times root log k, we get an algorithm. So the runtime of the algorithm was d to the o of t squared, So because we chose t equals log k, so we got a d to the order log square k time algorithm in this setting. Okay, so we beat this brute force algorithm that was running in time d to the omega k by somewhat, and we got like a quasi polynomial algorithm in k instead. Okay, it turns out that you can actually make this d to the log k with some effort, but again, we'll not do that today. Let's just focus on d to the log square k. Okay, does that make sense? So we didn't get a polynomial in d and k time algorithm. We got something worse, but something still much better than d to the o of k. Okay, so we'll call this a quasi polynomial algorithm in k. But actually, this does something interesting in a slightly different parameter regime too. So let's also look at that. So this was maybe example parameter 1. So here's a different parameter regime. Let's choose delta to be much larger. Okay, so let's say for some epsilon, you choose delta to be 100 times k to the epsilon over square root epsilon. Okay, and so think of epsilon as some small constant, less than 1/4, and less than 1/4 because I'm trying to understand, am I what does it take, how much time do I need to spend in order to beat this result of Wempal and Wang that worked whenever delta was bigger than k to the 1/4. So I'm going to choose epsilon to be less than 1/4. So now if you plug in the same thing, you see that t equals 3 over epsilon is enough to make small delta less than 0.01, which means that we get a d to the o of 1 over epsilon square time algorithm, in this setting. And so for any fixed constant epsilon, this is the polynomial time algorithm. So what we are saying is that, in polynomial time algorithm, we can, handle the case when capital delta is, polynomially large in k, even though the exponent of the polynomial could be an arbitrarily tiny constant. Okay, so in particular, even in fixed polynomial time, which could have been our gold standard, we are able to go beyond this k to the 1/4 result, that was known without sum of squares. So hopefully, there is some sense in which you see that there is what we're going to do today is valuable, because we are definitely improving on this result from 2002. So again, feel free to ask me questions, because before going on, I just want to give you attributions for this result, and then we'll move on to the proof. Okay, so these results were all proven in 3 sets of independent works in 2018. And so let me mention all these names. So the first set of authors were Raikkonen, Nicholas, Kane, and Stewart, and their algorithm does not use SOS. So their algorithm solves the problem we saw today, solves the problem for Gaussians. But it turns out, that the algorithm, in fact, the proof that I'm going to describe to you today will use very little about Gaussians, and so it will extend to more general distributions. And so, it will generalize to these distributions, which all satisfy a certain analytic inequality called as Poincare inequality. We will not, go into what this means at all today. But there's a much more general class of distributions than Gaussians that satisfies this inequality. And so, for all distributions that satisfy this particular inequality, it was shown in this work jointly with Jacob Steinhardt. And finally, so this was the SOS-based algorithm. In fact, I'm going to present something related to this today. An SOS-based algorithm was also discovered in this third, independent work for Gaussians of Hopkins and Lee. So all these, works happened in 2018. So what I'm going to tell you today is actually not based on any of these works. So I'm going to actually present you, some simplified proof, a proof that is simple enough that I can actually hope to complete it, in the remaining time today. That appears in this monograph with Fleming and Pitasi. And that's also actually a good reference for, looking at the details, etc., for what I'm going to talk about today. So this so that's basically the proof I'm going to present today. Okay, the proof from this particular monograph. Good. So any questions so far before we dive into the proof?
So this failure probability of 1 over D, is this just the characteristic of the problem or from SOS algorithm?
As in this, so okay, so let's maybe clarify where this, so maybe you're talking about this 1 minus 1 over D, the success probability, right?
Yeah.
This one. So so this probability, first of all, is only over, the draw of the sample. This, like the algorithm itself is going to be completely, well, okay, there is some randomization, but you could take care of, you could try to do this algorithm without any randomization at all, even though the one I'm going to present to you today has some randomization. So this probability is exclusively essentially over, the draw of the sample. And so it's going to, in some sense, you can imagine that, you will not succeed when the samples are somehow, satisfy some weird rare event that might happen. And so, this 1 minus 1 over D is actually just some innocuous thing, just saying that, the sample you see is typical. You can make it, I think, you can make it much smaller if you like. This 1 over D is just something that I'm going to be able to prove simply.
Okay. So at least this much probability the instance we get is pretty good. I mean.
Right. You're saying that, in some sense, this algorithm is going to work whenever the input you get is typical. And, with like 1 minus 1 over D probability, the instance we get is actually going to be typical.
Yeah.
Okay.
I have
Excellent.
a question.
Yes.
The number of, are we thinking of n as growing or
N is the number of samples.
so the time doesn't depend on n?
The time actually depends. Okay, very good. So I did some trick where I could write a shorter statement, but the running time actually is n to the O of t. So I should say it this way. So let's be more careful to answer Mithali's question. So the running time is actually n to the O of t. But this algorithm will work only when n is bigger than some n naught, which grows as d to the t. And so together it gives you a running time of d to the O of t squared.
So that that running time is like for finding the means, or like how is the problem defined for, as in
I will not be able to cluster if you give me too small a sample.
okay.
So yeah, so the algorithm only succeeds when you give me a large enough sample. Good. Any more questions?
I had a question.
Yes.
Is there any computational hardness known if delta is between like log k and poly k?
As in the gap between polynomial in D and K and quasi-polynomial in D that we are proving today?
Yeah.
It's a very good question, and I guess I was planning to spend some 10 minutes at the end on it. But basically, no. The answer is that we have no published sense of computational hardness here, but there is some some natural sense in which you can reduce some other average case problems for which you might have some believable hardness to this problem. Again, all these are like speculations, so I tend not to focus on those. So yeah, there is some weak sense in which you could say that this is inherent, but yeah, but there is no, I would say there is no credible sense in which this problem can, like, there is no credible sense in which you can't get a polynomial time algorithm here. And so yeah, that's an outstanding open problem. And if I get a chance, then I'll specify one way to make progress at the end. Good. Any more questions? Okay, good. So then let's discuss how we are going to prove this. And I told you, like this using this problem is basically a disguise for me, because I want to explain to you this method of designing algorithms. And so what we are going to discuss now, this approach for designing algorithms for this problem, would be more general, in the sense that it's the same approach that appears in essentially every one of the problems we discussed at the beginning of the lecture, and also more. Okay. You can in fact think of it as like some general blueprint for a class of average case problems, and it will become clear what class it applies to once we discuss more and more details of this procedure. Okay. But and as I promised you earlier, I will not pontificate on the generalities of the method. Instead, we'll uncover it piece by piece only for our application today. So the piece I want to reveal right now is that the idea of this algorithm is to focus on something related but simpler problem. So what does that mean? What problem are we going to focus on? So, in general, we are solving a certain search problem, right? Like we are given some samples and we're looking for a good clustering or an approximate clustering of the samples, right? We are going to instead focus on the following simpler problem, where, in addition to the samples, that we were given as an input in our problem, we're also going to be given some purported cluster. Let's call it C hat. Okay. What does that mean? Like imagine that, there was an oracle who you could just go and ask for solutions. Okay. So you said, hey, I'm like really stuck on this clustering problem. Can you help me? And the oracle says, yeah, well, here's a cluster. There, I solved your problem. The oracle gives you this cluster, but you are like saying, how do I trust the oracle? I don't quite, know if they're telling me the truth. Maybe it was like some genie in a bottle or whatever that you found in some shady location. So, it could be a good genie or bad genie. You don't quite know. So, you have this cluster in your hands, and, you just want to check if, what you've got is even the truth, right? You want to check if, hat C, it's weird, when you, so when I'm writing in pen, it's C hat, but when you write in LaTeX, it's hat C, and, um, yeah, okay, whatever. Okay, so you're given C hat, um, and you just want to verify, whether C hat could be close to a true cluster. Is the oracle lying to you? So this problem we're going to call, the problem of certifying whether a purported solution is close to a good one. Okay. Now, how can you do this? Well, what you can do is like you can make some sanity checks, on C hat, right? So you can make some sanity checks on C hat. And your hope is that, if C hat passes this sanity checks, then, it better be close to a good cluster, right? And your goal would be to prove if C hat passes these checks, then it's close to a good cluster. So what can you use in this sanity checks? Well, you have your input, so you're free to use that input in whatever way possible, right? So in generating, so let's call this sanity check a test from now on. Okay, let's call this a test for solutions. Okay, so this test in particular can use the input sample given to you in any way, right? Like you can use x1 through xn because they're in your hands. You can build a test using those, x1 through xn. Now, what should be the properties of a good test like this? So a good test should have two properties. And there are obvious properties, as you might imagine. Any true cluster should satisfy it. Any true cluster should pass the checks. So all true clusters C1, CK, if the oracle hands over to you the actual true clusters, then your test should be such that you don't reject them. So you should definitely design a test which has this property, and this property has a name. We'll call it completeness of the test. Okay, good. And we would like, but that's not enough, right? Like to design a test that where every true cluster passes, you can simply design a test which says yes all the time. So of course such a test won't be useful. So you would want, in addition, that if C hat passes the checks, then C hat is close to some true cluster. Okay, and given that given that we know the clusters were of size exactly n over k, we of course always force C hat to be of size n over k. That's without loss of generality because we know the true clusters are of that size. Okay, so this second property also has a name. We'll call it soundness of the test. Okay, and these names might remind you of things from formal logic. As you can see, there are overtones of formal logic in many of these lectures, and there's a good reason for it because what we are really using is a proof complexity approach to algorithm design. But again, we will not make this connection explicit, etc. We'll just like let it remain as undertones. Good. So we want to design a test using the samples that we have that has the completeness properties and completeness property and the soundness property, right? And if such a test exists, then what happens? If such a test exists, well, it's not clear at all how it relates to our goal of designing algorithms. But one thing that's immediate is that if such a test exists, then there is a finite time algorithm for the problem. For our problem, where there is no oracle. Why is that? Can somebody unmute themselves and tell me why I get like some brute forces algorithm that at least works if there is such a test?
You can just brute force over clusters and hand them to the test. And if it passes, take it.
Absolutely, right? Like, I can just simulate the oracle myself. The oracle is at best doing an exponential time computation, just go over all possible subsets of size k from the n points that I have. That's like n choose k different points, and just run the test on each of those, right? If the test is indeed complete and sound, then I will not accept anything. I will accept for, I will definitely accept true clusters, and anything that I accept will not be, far from a true cluster, right? And so, which means that, at least I get a finite time algorithm immediately if I design such a test. Okay. Now, in general, we shouldn't expect that whenever such a test exists in general for problems, we shouldn't expect that, we can always simulate the oracle in polynomial time. Can somebody tell me why should we have such conservatism? Why should we not always expect to simulate the oracle in polynomial time? It's kind of a trick
If
question.
we can do that, then we solve NP problems.
Right, exactly, right? Like, you can certainly check if an assignment satisfies the 3-sat formula in polynomial time. So you can design this test for, 3-sat very easily. And so if you were able to always simulate the oracle in polynomial time, then, you would prove P equals NP, which, certainly is not our goal in this class. And we also don't expect it to be true. So in general, we don't expect that whenever such a tester exists, that there is also an algorithm to solve our problem. But the nice thing is that if we impose certain additional conditions on the tester, we would end up in a world where, whenever there's a tester, there is in fact also an algorithm that precludes the need for this oracle completely. Okay, and that's how, we'll bring sum of squares into play. So, one somewhat glib way to put it would be that, um, we are going to work in a world where somehow P equals NP, because, we will design algorithms by simply designing tests, and then we'll always be able to, simulate the oracle in polynomial time. Okay, so that's of course a glib way to say it, because we are going to put additional conditions in the tester. So what conditions are we going to put? Well, we'll see in a we'll see in due course of time. But let's just say it this way here. If the test satisfies some extra conditions, then we'll always be able to obtain a polynomial time algorithm to simulate the oracle, and thereby obtaining a polynomial time algorithm to solve the problem. Okay, and so the high level approach for average case algorithm design using sum of squares is to simply focus on the task of designing a test which is complete and sound. Well, of course, we'll need extra conditions. We'll discover what those are in a second. But the first cut of the algorithm designist here is to forget about algorithm design and simply to focus on building a test, a certifiability test for true solutions. Good. All right, very good. So let's come back to our question. How can what test should we build? How can we check that a given C hat is a good solution? So for us, a solution is a cluster. So how can we check if good approximate cluster? So we don't quite know the means, so we can't quite use means in designing this test. And the constraints are that our test should be such that the properties that we check should always be satisfied by true clusters, and somehow they should also be enough that any set of points that satisfies those properties should be close to a true cluster, right? So in principle, we can check any property that holds for a true cluster, right? Because any set of properties that hold for a true cluster will always satisfy completeness. And our hope would be that enough number of those properties would be enough to even guarantee soundness, right? Good. So let's see what can we check. So of course we can check that C hat is of size n over k. We know that that's a property that's satisfied by all true clusters. So checking that will not violate completeness. So that's reasonable. But now, we want some property that really truly distinguishes fake clusters from true clusters, right? Like we would want some kind of check that, all true clusters pass, but, fake clusters somehow cannot. Okay. And to motivate this, let's recall our, drawing from earlier, where we observed that, at least in one dimension. So let's, to motivate this check, let's focus again on D equals 1. And if you focus on D equals 1, we talked about how the mean separation we have, this delta bigger than like root log k or whatever, somehow guarantees that the samples are the points from different clusters are completely essentially non-overlapping, right? So if I were to draw a diagram, it would look like this. So we have these lines, we have this mu1, we have mu2, and we know that we know that the gap between them is some large number delta. And if delta is large enough, we in fact know that these points look like this, right? Like we have some points from the first cluster here, and we have some points from the second cluster here. Of course, some points can deviate, but this is how roughly the picture looks, right? So now we want some property which if you test that property for the points here, then it should pass. If you test the property here, it should pass. But if I give you let's say these weird set of points where you choose some part of this yellow cluster and some part of this red cluster, and you intersect both of them appreciably, then this cluster should not pass it. This particular set of points should not pass it. So can somebody unmute themselves and guess a property like that? Or what's the difference between this purple set of the purple bracketed points and the yellow and red points? What's somehow a property that distinguishes between these two kinds?
Like a variance.
Right. That's a who was it? Who was that, by the way?
Tie.
Okay, Tai, you're absolutely right. It seems like so Tai's observation is that it seems like the yellow points are kind of close together, the red points are close together, but it seems like if I take enough number of points from both yellow and red clusters, then I'll have points which are kind of spread out because the clusters were separated, which means that I should expect more variance in this purple bracketed points, right? And so a natural idea is to just check if the variance is somehow appropriately upper bounded. So that's Tai's idea. In fact, that's a great idea. Test that C hat has appropriately bounded variance. Okay, and in fact we can determine what that appropriate number is also very easily, right? So but before that let's set some quick notation. Let's call mu hat is simply the mean of mu of C hat, which is simply equal to k over n, the empirical mean of the points in C hat. Okay, because I'm looking at variance, I have to look at around I have to look at the variance around some point, and I'm just going to look at the variance around the mean of C hat. Okay, so then Tai's idea is compute this number k over n. I is I in C hat xi minus mu hat square, right? Now let's try to understand what should I compare it to. If I was a Gaussian cluster, if C hat happened to be, let's say, one of the true clusters, then what would this quantity look like? Well, we expect that if I take large enough number of samples, then mu hat should be close to the true mean of that cluster, and the empirical variance should be close to the true variance of the Gaussian it was generated from, and the variance of my each of my Gaussians was 1, right? So I expect that this quantity would be not too much larger than 1. So in principle I can say it's smaller than 1.1 if I allow large enough samples, right? And this 1.1 is just to allow some sampling error. Okay, so now I claim that if I have a typical looking sample and I check if this variance is smaller than 1.1, then all true clusters will pass it. And well, of course, we don't quite know if fake clusters are rejected often enough, but it's certainly a test I can do. Is there any issue you see so far that's confusing in this idea? Notice that in doing this check, I did not need to know anything about the true means. All I did was I took the points in C hat, computed their empirical mean, and then computed the variance around that empirical mean and checked if it is like smaller than 1.1. Any questions about this? Good. So actually, I can go a little bit beyond Tai's idea, or at least just extend the idea in the following way. Instead of checking just the variance, I can check some higher moment of the deviation around the mean. So more generally, for some parameter t, I can check that the empirical deviation around mu hat, if I, let's say, so I just want even powers here so that I don't want some sign cancellation going on. So I can check, 2tth, moment of empirical moment of the points in C hat. And again, if I have large enough number of samples, large enough points in each cluster, then this should, for any true cluster, should converge to the true 2th moment of a Gaussian. Can someone tell me what that number looks like? What's the 2th moment of a Gaussian with variance 1?
like 2t minus 1 double factorial, and roughly
Right. So
t to
yeah.
the t.
Yeah, absolutely. So, Tim is absolutely right. So, by the way, like, I don't know if you've seen this double factorial, but Gaussian moments have very nice algebraic structure. You can actually, think of the like Gaussian moments as they are related to actually, number of perfect matchings of certain graphs. So there's like nice combinatorics behind these moments. Again, for us, it doesn't matter, how these numbers can be generated. All that matters is that, for standard Gaussian, with mean mu and variance 1, this number looks like, in fact, is exactly equal to 2t minus 1 double factorial, which, by the way, is just the product of all odd numbers less than 2t. Okay, and this number, so it's like a product of roughly t numbers, right? Like it's the product of about t numbers. So it's not a surprise that it grows as about t to the t. Okay, in fact, t to the t is an upper bound on it, I think, which means that I can just check that the empirical 2tth moment is at most some 1.1 times t to the t. Again, this 1.1 is to allow myself some sampling error. Okay, so now I have like a category of tests I can do, right? So let's summarize that in the following way. So this gives us one particular kind of test. It says accept c hat if and only if c hat is of size n over k, and 2, the empirical deviation moment around this mean is at most 1.1 t to the t, where mu hat is mu of c hat, just the mean of points in c hat. Good, makes sense. And so it's not much of a surprise that if I choose large enough samples, then the true clusters will satisfy this. Let's just quickly note that before moving on. So let's like for completeness, so okay, let's maybe make a definition so that I can use it again. So let's call, so I'm just like trying to identify the property of a typical sample under which all true clusters will pass this check. So I'm going to define a sample t delta good. Okay, so I'm going to call input sample t delta good if also I'm looking at the sample I'm calling, so I'm looking at a sample which has this true cluster partition C1 union up to CK, right? And X has endpoints, each CI has an over K point, so same notation, right? And let's say the true means, okay, and let's say mu hat I are the means of CI. Okay, for every I. Then I'm going to call this sample t delta good if for every r not equal to r prime. Okay, let me write down the condition for high dimensions, even though we'll focus on d equals 1 for a bit. So this is saying that so this property was satisfied. So earlier we asked for this separation property for the distributions, but now I'm asking for it to hold for my sample. So I'm going to call my sample t delta good if this happens. Very good. And 2, if I look at the empirical deviation around the empirical mean for every cluster, then it's not too much larger than what I expected. Okay, so I just abstracted out the two properties I wanted from my sample, the two properties in which I wanted my sample to resemble the distribution that generated it, and I just abstracted out into this definition of t delta good. Okay. Now, really, truly speaking, if my distributions were delta separated, like if the means in my distribution were delta separated, then I will not get capital delta here. I'll get something tiny number, delta minus some small number. But let's ignore that distinction because that would demand that I, introduce some more new notation. So let's just forget about that and just call it delta. Okay. So up to that fudging of delta versus delta minus something small, do you all agree that this is a property that at least you would imagine a large enough sample from, my distribution to satisfy? Because I'm not going to prove it. I'll just state it. If, n is larger than k over delta square log k over eta, then, and mu1 through mu k are delta plus small delta separated, then with probability 1 minus eta, an n sample is t delta good. Okay. Again, I'm not going to prove this. This is just a simple exercise in using the Hovding bound correctly. Okay. So that's all I'm going to say about this, but hopefully that's reasonable, right? Like feel free to ask questions if this is confusing, but all I'm saying is that, if I take a large enough sample, then, the points I see will pretend to be Gaussian in the two relevant properties I care about. Good. Very good. Once I have this, the completeness part should not surprise you. The completeness says that, if, x1 through xn is t delta good, then, every good sample, every true cluster passes the checks. Okay. And so the non-trivial part, of course, is, the soundness, which is, why, if at all, are the checks we made enough? Okay. Why are they enough to somehow, kill every potential fake cluster? Okay. So let's, focus on that. At least write down the theorem statement. So again, so let's actually give this x1 through xn the name x. Okay. So let x be, a t delta good sample. And let, C1 up to CK be true clusters. Of course, I don't know these. So, I can't quite use it in my algorithms, but they're just going to appear in my statement. Okay. So let C hat be any, collection of points so that one, they are the right size. So I'm basically writing on the condition that says that, C hat passes the tests I just designed. So let's say C hat is of size n over k, and 2, k over n, sum over I. Okay, sum I in C hat, xi minus mu of C hat to the 2t is at most, this number that we chose so that, true clusters definitely satisfy these checks. Then, so now, I want to say what? So let's maybe make sure that we formulate this correctly. We want to say that C hat is close to some true cluster. We want to check, say that, if C hat passes the checks, then, C hat must be close to one of the k different true clusters. Okay. So I'll write it as max R at most k, WCR is at least 1 minus delta. For delta oh man, my scribble has erased the exact non-trivial part. Okay, so I'm going to guess and then hopefully we'll be able to prove it. I hope that was the exact same thing I wrote earlier, because somehow that part in my note has gotten erased. But we'll see. The proof will be transparent enough that we can recover it. But what we are saying is that the exact kind of accuracy guarantees that we wanted are at least satisfied by this tester that we built. So this tester actually is good enough if t is large enough compared to delta. So does the statement make sense? Let me pause and make sure that you understand why this is soundness, and at least qualitatively it should make some sense. It's saying that for any fixed delta, if I choose larger than like some c root log k, if I choose t large enough, then in fact the checks that we just discovered by just eyeballing how the samples look like in one dimension, in fact are good enough. Notice that we only formulated the test right now for one dimension. We're going to look at what happens later on for high dimensions in a bit. Okay, so far we are focusing on solving a very easy problem that we already saw some greedy clustering solved it. Okay, but we are looking at this easy problem because we will be able to generalize it to high dimensions very easily. So let's come back and look at the soundness, and let's take any questions if there are any. Okay, so no questions. So let's see, what's a good thing to do? Okay, let's maybe do the proof of this soundness, and then we'll take a break. Okay, that would be a good stopping point. So let's prove this soundness. Good. Let's see what's actually maybe a different thing is better to do before the break. Instead of proving the soundness, let me make a different point, which is how this test actually relates to an algorithm. Okay, so we've actually seen a test now, and we have written down at least the soundness and completeness properties of it. The completeness is believable, the soundness requires proof, but we are going to focus on it in a second. But now, let's try to uncover this mysterious properties that I said at the beginning. I said that if the test is somehow nice, like satisfies some extra conditions, then it would relate to algorithms for us. Okay, and it's especially how SoS is going to come in, right? So I guess the nice part is, so let's observe why this particular test is nice. Okay, first, the purported solutions can be written as vectors in Rn. So what are the solutions to my what are the kind of solutions I'm hunting for? I'm hunting for clusters, right? So even though there were subsets of points, I want to point out that they can be seen as just vectors in Rn. Why is that true? Well, for every c hat, I associate c hat to the indicator, like the 0, 1 indicator of whether each sample is included in c hat or not. Okay, so think of the variables w1 up to wn, and wi is 1 if and only if ith sample is in ci. Okay, so you agree that I can at least think of the solutions I'm hunting over as n dimensional vectors. I mean, they happen to be just 0, 1 coordinate vectors, but certainly vectors in Rn, right? Good. So that's good. The second thing I want to observe is that the checks I made, the checks in my test, are polynomial inequalities in WIs. So I'm now making a claim that the things I'm checking, the thing I'm testing for, so I guess we have a guest joining our class today.
Yeah, he's very interested.
Yeah, maybe he'll find a better clustering algorithm. All right, okay. Right, okay, so good. So I'm going to observe that the checks I'm making are in fact polynomial inequalities in WI. So why is this true? So what are the checks I made? The checks I made were simply that the number of points I chose are n over k, right? So that just means that some WI should be n over k. Then the other thing I checked was, that the empirical, the 2/10th moment of the deviation around empirical mean of the points indicated by W is, appropriately bounded. So that mouthful of a statement can be written as follows. Look at the linear polynomial in WIs. Then notice that this is simply the mu hat we have been writing. Right? I just like this WI, if it's really truly an indicator, then it picks out the points which are in C hat, right? And then it averages them. So it is definitely the empirical mean of C hat. Good. And the check I made was, hopefully you will also agree here, so this happens to be, let's see the degree of this polynomial, but I hope it's already clear that it's a polynomial, right? So this inside expression is a polynomial of degree 2t in W's. Then I have one more W outside. So this is a degree 2t plus 1 polynomial. Still good? Still agree with me? Again, feel free to stop me. But I think only thing I'm observing right now is that my solutions are vectors. The tests, the checks I made on the purported solutions are polynomial inequalities. And just to check that you're all following, I think I missed one check here. What's the check I missed? Why are the polynomial inequalities I have not enough?
WI should be indicators.
Right. I never forced that WIs are 0, 1. I just said they are real vectors. So I need to somehow encode the property that WIs are, either 0 or 1 valued. And, I want to, in fact, do it using polynomial inequalities. So what would I do? Well, I'll just add the polynomial equality checks that WI square equals WI for every I. Okay. So now you see it's a perfect translation, right? It's a perfect translation of the checks I made on C hat. Feel free to stop me if this is not clear, but all we did was like just translate a notation into this W, the indicator of C hat. Good. The third property I want to, yeah.
You also need to check with like each I is assigned to only one cluster, right?
The solutions I'm looking at are exactly one cluster. I only have
okay.
I'm not checking a clustering, I'm checking a single cluster.
Okay.
Good. So yeah, I'm going to just try to verify if a given set of points forms one cluster. I'm going to do this one by one if you want, okay? Good, very good. And the final thing I want to observe is that the conclusion of soundness statement about the test can be written as a polynomial inequality. So let's go back and check the conclusion of the soundness statement. This is only like slightly non-trivial. I mean, at least it's not immediate like the other things. So the conclusion of a test was, the conclusion of the soundness statement was that, the maximum intersection, oh no, I guess nobody stopped me when I using this weird notation where I was getting ahead of myself. But the conclusion is that the max intersection of C hat with some CR is large. is this a polynomial inequality? It's not a polynomial inequality because, okay, if I remove the max, it's certainly a polynomial inequality, right? It's saying that, if I sum up the wi's, okay, let's try to do this, okay? So if I want to phrase this statement, then, I can write down a polynomial inequality corresponding to it. You agree that, if I wanted to phrase the statement that C intersects the true cluster CR in 1 minus delta fraction of the points, then that's equivalent to this polynomial inequality, in fact, a linear polynomial inequality in W's, right? But I don't quite have this. I have max outside here. Max of a bunch of polynomial inequality is not a polynomial inequality in W, right? But, we'll just do a slight trick to make it one. So what will we do? We'll define the following quantity. For each R, define W of CR to be, the fraction of points in C hat that come from C sub R. Okay? Then I'll just write the max conclusion in a slightly different form, or at least it's slightly, okay, let's maybe just write down, instead of pontificating, R equals 1 through K. Actually, before even writing that, and just to check if you're all following, what is this sum supposed to be? If I sum up WCRs from 1 through K, what should I get? Remember, WCR is a fraction of points from C hat that intersects C sub R. What happens if I sum up all of these fractions?
1.
Yes, but do all of you see it, or is it like, because Tim has been unmuting himself a lot? Okay, Misha is vigorously shaking his head. Either he's head banging or he's saying yes. Okay, very good. So you all agree, because every point is in some cluster. So I added the fraction of points from, C hat that come from each of the clusters. Of course, if I add them, I should get all the points. So the fraction should be 1. Good. Now consider the following inequality. The sum of the squares of WCRs is at least 1 minus delta. I claim that, up to some delta versus 2 delta difference, this is actually equivalent to the max being large. Why is that? So first of all, I want to claim that if this inequality is true, then it implies again, somebody not Tim, tell me why this is true.
A quick question. Why is this 1 and not K?
Say it again.
Why is the equal to 1 and not K?
Because WCR is a ratio. WCR is like the fractional intersection with C sub R.
Oh, I see. Okay. The K cancels. Never mind.
Yeah, makes sense? Okay, very good. So yes, so Jason, can you tell me why this square inequality implies the max inequality? Okay, it's only slightly confusing, so let me maybe just like quickly do it. Okay, so so look at this quantity WCR square. Okay, then write it as WCR times WCR. Big difference there. And then observe that I can upper bound this by WCR times max over R of WCR. Agree? And so what I have now gotten is and we convince ourselves that this sum on the left hand side, the first term is 1. So, what have we proven? We've proven that, the sum of the squares of WCR is in fact, upper bounded by the maximum over all R of WCRs, which means that if the sum of the squares is larger than 1 minus delta, then so is the max. Is this convincing? Good. I'm going to assume it's convincing. So that gives us our final, point that I was making here, which is that, the conclusion of the soundness statement also happens to be a polynomial inequality. It wasn't so when we wrote it at first, but at least if I, massage it and write it as the sum of the squares of WCRs being large, then in fact, it is a polynomial inequality. Okay. So let's go back and check the solutions for vectors, the checks for polynomial inequality equality checks, and the conclusion of the soundness was a polynomial inequality. Okay. These are, in some sense, these are observations that are true about our test, but are also, in some sense, the basic conditions a test must satisfy for our algorithmic ideas to our approach to actually yield algorithms. Okay. So the special kind of test we will consider are tests where the checks are polynomial inequalities, and the conclusion of the soundness of the test is also a polynomial inequality. Okay. And in fact, what we're going to prove later on is that, so, what we're going to prove later on. So this is like loose but informal statement. If test satisfies above, in fact, let's define some piece of notation right away. That the polynomial inequality checks we made on W in our test, I'm going to call, so it's a system of polynomial inequalities now, right? So I'm going to call all of those checks by script AW. Okay. So now I can come back and say the informal statement here, the test satisfies all the conditions above and AW derives. So, because the conclusion of the soundness is a polynomial inequality and the checks I made are a polynomial inequality, I can ask if there is a low degree sum of squares certificate or proof that derives the conclusion of the soundness, the polynomial inequality appearing in the conclusion of the soundness from AW. So I can ask if there is a low degree proof of this. And so remember the notation we developed the last time was, we wrote down the degree of the proof at the top. So what we're going to eventually establish today is that, not only is there a proof of the soundness statement we wrote earlier, in fact, AW derives this conclusion of the soundness in not just any proof. In fact, it derives it in a sum of squares proof of degree at most 2t. And we're going to show that any test which satisfies all the properties above, including the fact that the soundness statement can be derived as a low degree, as a low degree sum of squares conclusion from the test checks. If this happens, then in fact, we can obtain an efficient algorithm for finding W's that satisfy the checks. And, of course, for us, those are clusters. So, what this is saying is that if there is a low degree sum of squares proof of soundness of the test, then in fact, you can get an efficient algorithm for finding something that satisfies the test. And so, at an informal level, this is the sum of squares approach to average case algorithm design, to somehow come up with a certifiability check which can be encoded as polynomial inequalities and show that the conclusion of the soundness of the test can be, obtained by a low degree sum of squares proof from the checks, the polynomial inequalities that appear in the checks in the test. And then, you will see that in some sense, you can essentially, in a black box way, use this statement to design an algorithm, using sum of squares to, calculate W's which are good for you, which are solutions. Good. So let's take a break, 10-minute break as usual. We'll resume at 5:57 and we'll do a proof of soundness and derive an algorithm from it.
So I had a question, like I still I'm having trouble with the k e to the negative delta squared thing. Like I still don't understand where the k comes from.
Which
Like
key?
way back when, like the heuristic. I didn't want to give it time.
Okay. Yeah, let's.
Because like as far as like my intuition is telling me like okay, each point has probability like e to the negative delta squared of being wrong.
Yes.
And so the fraction of points, that are wrong is like e to the negative delta squared.
It's a perfect intuition, but let's understand what is like the fraction that you're considering is over what. You are interested in making an error, in terms of so let's look at the cluster number one. The cluster number one is of size n over k. Okay.
Mhm.
So you are interested in making an error. So the erroneous point should be at most delta times n over k. In something that I recover, so the number of points that I'm actually okay to make an error on is only delta times n over k. As a fraction of the total number of points, that's at most delta over k.
So Misha, the point is that like you're wanting a stronger conclusion, which is that like not the total errors at most delta across all points, but like within each cluster, the error is also at most delta.
The other statement is not even meaningful, right? Like if the total error being small doesn't give you anything. You're like the only way the conclusion is meaningful is if there is some cluster that at least captures majority of the points in C sub 1. The only way that will happen is if like if you look at the points which are not in cluster number 1, then there are a lot more than the number of points in the cluster, right? 1 minus 1 over k times n points are outside cluster number 1. Each of them can be erroneous with e to the minus delta squared over 8 probability or whatever, right? So you would want that these 1 minus 1 over k times n points together should contribute at most delta fraction of the first cluster, right? And the first cluster has n over k points. So
then we're like then we're just like upper bounding crudely, like with the saying like okay, each thing is gonna appear in that cluster with that probability.
Yeah, so all we are using is that every pair was like delta far. You're right. Like we could be a little bit more fine grained and instead use the distance that we have. But yes, for the heuristic reasoning, this is reasonable, right?
So then, like in 1D, like wouldn't it only? Oh wait, it's gonna be I see, okay.
Yeah,
that makes sense.
You are by the way right, Misha, that because of the geometry of 1D, it can't possibly be that there are like k more than 2 points which are all delta far from each other. That's a perfectly valid point. But remember that our conclusions have to be valid in higher dimension, and then I can certainly find points which are all at a distance of delta from each other.
Okay, that makes sense. Okay, I was also centering on 1D.
Yeah. In 1D, you can certainly do a lot better. So the heuristic reasoning is not the tightest possible thing to do in 1D. But in high D, at least it's imaginable that what we did is essentially the best you can do.
Okay, that makes sense.
I had one last question.
Yeah, of course.
So the like the lower bound you said was not actually for the error, right? Like the heuristic calculation was for the error probability, but the lower bound was for the sample complexity.
So yeah, I'm proving something stronger. I'm saying that if you wanted to do this, then not just the running time, but even the samples would need to be large. If the samples are large, then certainly running time needs to be large, right?
Yeah, but it's not like the that you cannot do it at all, right? If delta is smaller than square root log k, then you will screw up like one whole cluster. This is like a different statement than the samples complexity.
Okay, so right, so you're pointing out a different problem where we might not want to recover all clusters. We are interested in a slightly different guarantee where you want to recover, let's say, most clusters, but it's like scrambling one full cluster perfectly, right? That's a reasonable goal. In fact, so one of the papers I mentioned, so there were like 3 attributions. The paper that we the paper with Steinhardt that I mentioned actually solves that slightly more general problem that you just mentioned. In fact, it solves the so-called list decodable mean estimation problem, which in particular includes what you asked as a special case. And so yes, so you can go beyond the kind of clustering guarantees we are looking for today. But yeah, I'm not going to prove that. Yeah, I'm not going to prove that today. Yeah.
Okay, thanks.
All right. So good. So I just rewrote the soundness in terms of these polynomial formulation that we just discussed, right? So that's just a restatement of the soundness we saw earlier. So what we'll do now is just like prove it, and then make this informal statement that we wrote just before the break right here precise. Okay. All right, let's do it. And the proof itself is actually very simple. Okay, so in terms of one of the reasons I chose this example is because every the technical parts are really simple. So hopefully I will not lose any of you here. Again, feel free to stop me and ask questions if I do. Okay, so look at the conclusion of this statement. I want to somehow say that if W satisfies the checks in AW, then in fact sum of WCI squared should be large. Okay. Oh, actually, one thing I want to mention even before going here is that notice that the statement of soundness does depend on the true clusters C1 through CK that I do not have any knowledge of. Okay. But that's not, like if at all that's somehow confusing, notice that it's the checks that I have to do that I have to somehow, so the checks I do, which means the description of the polynomial inequalities in AWs, they cannot depend on mu sub i's because, those are the checks I have to make. I'm the verifier here. So I have to make those checks, which means that and since I don't know mu i's, I cannot use them in AWs. But the conclusion is perfectly fine, right? Like the conclusion of my checks, depending on CIs, is not at all a problem, right? It doesn't mean that I need to know CIs for implementing my test. Hopefully that's clear, okay? Notice that, the WCIs here are the true clusters here, but that's not a problem. It's only in the conclusion that the CIs appear, not in the test. All right, so let's go ahead and prove the soundness. So the first thing to observe is that, if I look at this number, WCI, then you remember it was 1, which means its square is also 1, right? And if I square it, I get two kinds of terms. The square parts that I like, and then there are these cross terms. Right? Which means that if I have to prove that the first term is large, then all I have to do is to prove is that the cross terms are small. That's equivalent, right? So that's what I'll try to do instead. So I'll try to upper bound. So now my goal would be to upper bound, all the cross terms here. Good. All right. So let's do that. So the first thing I'll observe is the following, weird transformation, but, a correct one. So can someone tell me why this is a legit thing to do?
Mu r minus mu r prime is at least delta.
Exactly, right? Like mu r minus mu r prime is at least delta. So, I have basically, for each term, for each r and r prime, I have multiplied WCR times WCR prime by mu r minus mu r prime to the 2t divided by delta to the 2t. And this quantity is at least 1 for every r not equal to r prime. Right? So this is certainly an upper bound. Good. All right, so that's that's some potentially weird thing to do, but you'll see it's helpful. And now I'm going to use a really famous and complicated inequality. I'm going to call it the almost triangle inequality. It's the most complicated inequality I'll use today. So let's write down what it means, okay? It means that a for any a and b, a plus b to the 2 times t is at most 2 to the 2t minus 1, a to the 2t plus b to the 2t. Okay? And this should not, I mean, I'm sure you can see a proof of this already, but let's see some special cases to make sure that you don't you don't think this is some weird thing. So if I look at it for t equals 1, this is saying that a plus b square is at most 2 times a square plus b square. Do you all agree why that's true? Do you all see why that's true? Actually, just for kicks, let me give you my favorite proof of this inequality. My favorite proof of this inequality is 2 times a square plus b square equals a plus b square plus a minus b square. Okay, so I have proven a special case of this really complicated inequality. I hope you're all enjoying this show I'm putting up. This is great. And actually, you can just iteratively use this equality that I used to prove this inequality above here to basically, okay, so let's maybe do it one more step, okay? So I'll do one more step of this because talking about it is more complicated than doing it. So I write it like this. And then, I apply this inequality that I proved to both those terms. Okay? And then I apply the inequality again to a square and b square instead. So I get that this is at most 8 times a to the 4 plus b to the 4. Wait, did I do that right? Well, I hope I did. Okay, good. So actually, I can use some simple reasoning like this to, I think, prove this inequality for every, every exponent which is a power of 2. But actually, you can prove it for all t here. And what you to use, or at least the one proof I know uses the AM-GM inequality. And the fact that arithmetic mean of a bunch of numbers is, at least the geometric mean. Okay, so I'm not going to prove it. I'm going to assume that you can prove this inequality, and I'm going to call it the almost triangle inequality. Okay, and I'm going to draw a box around it. Good. So let's use the almost triangle inequality at for this line, the star line here. Okay. What I'm going to do is write mu r minus mu r prime. So write mu r minus mu r prime as mu r minus mu of w plus mu of w minus mu r prime. For mu of w is basically the notation for the following quantity. It's the mean of the points indicated by w. Okay, so I can write mu r minus mu r prime this way. So which means that mu r minus mu r prime to the 2t using the almost triangle inequality is at most 2 to the 2t minus 1 mu r minus mu of w to the 2t plus mu r prime minus mu of w to the 2t. Still agree? Okay, this is the most complicated fact I'm going to use. So hopefully this is clear. Good. So if I now apply this fact, to this line over here, what do I get? I get that, the sum of the cross terms is upper bounded. So now, here was mu r minus mu r prime to the 2t. I'll replace it by this conclusion of the almost triangle inequality. I'll pull out this 2 to the 2t minus 1 outside here. And I write it as mu r minus mu of w to the 2t plus mu r prime minus mu of w to the 2t. Still with me? Good. So now notice that, the first term here does not depend on, r prime. Okay, so I can just like sum over r prime here. And even though I actually only have to sum over r prime not equal to r, if I sum over all r prime, it's only an upper bound. Okay, which means that for the first term, if I sum over all WCR primes, I get at most 1, right? A similar reasoning I can apply to the second term, which does not depend on R. So, I gather a factor 2, which I absorb in this multiplier outside, and write this as at most WCR times mu R minus mu W to the 2t. Agree? My whole proof is going to be just some simple manipulations like this, okay? We can discuss why it works, etc. right after that I do the proof, but I want to first do it. Good? All right, so next, what I want to do is, introduce the samples that I had, okay? Like right now, the expressions I have does not depend on the samples at all, right? Like the samples do not appear explicitly. So what I'll do first is to rewrite this statement, rewrite this, inequality, or rewrite this expression as simply the following sum. So now, the point is that, I'm summing up over all clusters here, right? In the inequality I already have, in the expression I already have, I'm summing up over all possible clusters. I'm going to replace each of these clusters by the constituent points, okay? So now what do I have? Or okay, maybe I can do it a little bit more slowly. I can write it as r equals 1 through k. Then I can write it as I in C sub r, Wi. Okay, so hopefully this step is absolutely clear, right? I just replaced WCR by what its meaning is. Its meaning is sum of Wi over I in CR times k over n. Still following? Okay, I just
Well, it seems like he's not following.
Who is not following?
Wait, you're back. I thought you froze.
Oh.
You like stopped talking mid-sentence.
Oh no. How long ago did that happen?
Like just 10 seconds.
Okay, that's good then. So do you all agree with this massaging of the line I have, this step that I did? It's all clear, right? I just replaced WCR by what it means, what the definition is, right? Good. So good. So now I want to just rewrite this line as sum over all points at once.
Okay, wait.
Instead,
you like briefly froze again.
Oh man, what is happening?
It was only like 3 or 4 seconds.
Okay, yeah.
Just like maybe start from where you're talking about the last equality that you're writing.
Yeah, I guess what I did is probably easier than talking about it. So all I did was I'm just rewriting the line here. I'm saying so let's look at what's happening to each point here. Each sample point I appears inside this. It multiplies mu sub r minus mu of w to the 2t, right? So the mu sub r is simply the mean of the true cluster that the ith sample belongs to. Okay, so now let's make the following notation. For every sample I, let C of I basically be the cluster that I belongs to. Okay, makes sense? So now with that notation here, each Wi multiplies its cluster mean minus mu of w to the 2t. That's what I wrote down in the bottom line here. I sum out from 1 through n. I multiply Wi by mu of C of I. Mu of C of I means, the cluster that contains the ith point minus mu W to the 2t. So still agree? Everything's good? Good. Because now, I'm going to yet, apply the almost triangle inequality one more time. Okay. And I'm going to upper bound this by 2 to the 40 times xi minus mu C of I to the 2t plus xi minus mu of W to the 2t. Okay, and this time what did I do in the almost triangle inequality? I'm applying it term by term. I'm applying it for each I separately. And for each I, I'm looking at this expression mu C of I minus mu of W. Okay, and I'm adding and subtracting the sample point x sub I. Okay, and then applying the almost triangle inequality. So again, stop me if I do anything, unverifiable here. Still good? Okay, because that's the last non-trivial step I have to do. Now, I'm just going to collect the terms correctly together. I'm going to pull k out and write this as I from 1 through n, wi xi minus mu c of I to the 2t plus 1 over n I from 1 through n wi xi minus mu of W to the 2t. Okay, very good. So now I claim that I can erase W and still have an inequality. Why is that? Well, Wi is at most 1. So, in the first expression here, I removed Wi. I just like upper bounded by 1. Okay, and because it was multiplying a square, this is a legit step to do. Okay. And now, I want to say that, I'm at a point where I can just upper bound both these terms separately. Okay. And let's see if you can help me do that. Let's try to upper bound the first term first. Okay. What is the first term here? So let's understand what's the distribution of xi minus mu sub ci, because that's maybe easier to look at. Okay. So remember mu sub, so xi comes from, one of the k possible Gaussians, and then you are subtracting of the mean of the Gaussian it came from, right? Because that's what mu sub c of I is. So what's the distribution of xi minus mu sub ci?
Gaussian with mean 0.
Exactly. So it's a Gaussian with mean 0 and variance 1. So each xi minus mu sub ci is actually identically distributed as a Gaussian with mean 0 and variance 1. So I actually have the 2tth moment of, a Gaussian here. And in fact, for a t comma delta good sample, we already, the definition already, implies that this should converge up to this constant factor loss that we were okay with to the true moment of a Gaussian. So this term is at most 16t to the t. Good. What about the second term?
We can get it by the soundness hypothesis.
Exactly. So here we are going to, we know that W satisfies the constraints AW, and the second check in AW is precisely saying that if I look at the empirical 2th moment of the deviation around the empirical mean of the points in W, then it's at most that of what it should be for a typical sample of a Gaussian. So this came because we had a typical sample. So we use that, here we use T delta goodness of X. For this one, we are using AW. This is simply a constraint in our program. So this is also at most 16 T to T over T to the T. But the reason for the two things are different. The first thing is true because our sample is good. The second thing is true because we put it as a constraint explicitly. Okay. But no matter what the reason, both these terms are, at most 16t to the t to the t, whatever. And so, if I did the algebra correct, now you can see that, I'm getting some exponential in t, and then I'm getting a t to the t, I'm getting delta to the minus t, and I'm getting a k. So I'm just going to write it as assuming that I did the algebra correct. Good. I don't know exactly how I got 512, but, not much different. So, that's it. We've proven soundness by a sequence of manipulations and 2 high-profile uses of the almost triangle inequality. Okay? So, the intuition for why this is supposed to work is simply what we already discussed. That, somehow, in a certain quantitative sense, the deviation of points in a true Gaussian cluster is supposed to be upper bounded. And so we quantitatively measured it using this, moments. And all this is just like some simple argument that, extracts the conclusion of the soundness based on the intuition we had earlier. That, really any cluster that, manages to satisfy these, moment upper bound should in fact be close to a true cluster. Okay. So now, given that we have a proof of soundness, I want to tell you about how this implies an algorithm. Okay. So let's do that. So first thing I want to claim. So I want to claim this is the corollary and not even try to prove it, just like hand wave very vigorously, is that, what we proved actually is that AW implies in degree 2t in variables W okay. So let's see why. Okay. So what we are going to use is that, the proof of this corollary is basically observing that the steps we did in the actual proof that we just, went through right now, each of those steps was actually a sum of squares inequality. As in each of those steps was proving, each of the step involved an inequality which was true with a sum of squares proof of degree at most 2 sub t. And then we are, combining them together by this calculus of SOS proofs that we wrote down the last time. That, if somehow if you do a sequence of SOS proofs, then you can combine them all into one and get a degree bound in the proof. So I'm going to hand wave here and tell you why this is true. But I think it's a very useful exercise for you to go back and, just try to unfold this whole calculus, like repeated proofs, and, see what the SOS inequality you proved turns out to be. So actually, what we are really proving is that if you look at this polynomial 1 minus delta minus I equals 1 through k WCI square, then this is actually a sum of squares in W. That's what we are proving. That's the claim. Okay, so even though, we proved that this is bigger than or equal to 0 in the proof, the claim is that, because every step is going to be every step is going to be a sum of square step, then, modulo the constraint. So, let me write on plus f, where f is in the degree 2t polynomials.
Wait, is this the opposite direction? Should it be the sum minus 1 minus delta?
Oh, yes. Absolutely. So the ideal of AW, I don't know if I used this terminology last time, is just, the polynomials that are, multiples, multiples and sums of multiples of polynomials that appear in A sub W. Okay, so let's not. So okay, I'll clarify this in a second. But let's, first go back and check why I claim that every step can be done, with a low degree sum of squares proof. Okay. So let's go back to the very first step. This step there is, I guess when I was introducing this notation, etc., the last time, I stressed on the fact that you have to be careful about what is a constant and what is a variable of the SOS proof. In the first step, there is nothing that we do to the variables. The W's are variables here, but mu r minus mu r prime and delta, they are constants. They are not indeterminates in the proof. So the first step actually is a trivial SOS proof because all you did is like multiply WCR times WCR prime by a constant bigger than 1. Okay. So the first step is, using, the great sum of squares fact that, for any polynomial f, which is non-negative, fw is less than equal to, cfw for all c bigger than 1. Okay, that's all the fact it's using, right? Like WCR times WCR prime can be upper bounded by WCR times WCR prime times mu r minus mu r prime over delta to the 2t. Okay, good. So what about the next step? The next step uses the almost triangle inequality. And actually, we didn't prove it, but the kind of proof I was suggesting is already a sum of squares proof in the variables a and b. Because look at the identity we wrote down. For at least the case of 2, we proved the inequality a plus b square is at most 2 times a square plus b square by literally writing down the difference of the two sides as a square. Okay, so this identity is a proof of degree 2 in the SOS system in variables a and b. Okay, and so now what you're doing is plugging in, for a you're plugging in mu r minus mu w, for b you're plugging in mu r prime minus mu of w. So you're using, the substitution rule of the calculus of SOS proofs that we wrote down the last time. Okay, so here we are using that almost triangle inequality has a degree 2t sum of squares proof, and that we are just like applying the substitution rule. Very good. So next, what did we do? Next, so this part was like just a simple summation. So nothing great happened here. Then we applied the almost triangle inequality again at some point. And the justification for that is literally the same, except that we use a different substitution for a and b. And finally, at some point we use the constraints, and for one of them we use the truth. So so notice that this is a constant in the proof system. There are no indeterminates that appear in the first expression. In the second expression, indeterminates appear, but our constraints imply that that is upper bounded. Okay, so with that vigorous hand waving, so all by the way, like none of these arguments are really complicated, but writing them will take me 20 minutes. So instead, I'm going to ask you to verify it, that all I said was like legit, and just claim that by simple calculus of SOS proofs that we wrote down the last time, and by the assumption that almost triangle inequality has a degree 2 sum of squares proof, which you will verify in the upcoming homework, we have arrived at the conclusion that in fact the proof we did is in fact a low degree sum of squares proof. Now it might appear like magic that we did something very reasonable in terms of the proof, like in real life. Like none of the steps that we did were like somehow constrained, like we were not somehow explicitly looking out to do a SOS proof. We did like fairly reasonable manipulations to these inequalities, and it happened to have SOS proofs because the most complicated fact we used was the almost triangle inequality, and it has a sum of squares proof. This is actually not just an accident but a trend. In many of these, in some sense, all of these algorithms, it turns out that we can essentially pick a more or less natural proof of a certain inequality you're trying to prove, and give a real life proof of it. And if if you set it up correctly, then the natural proof usually turns out also to be the SOS proof, or at least it's not too hard to SOSize it. Okay, we'll see exceptions to these kind of meta rules later on, but at least in this particular proof, it's not such a surprise that what I'm saying is true, that the real world proof basically was almost the way it was designed was already a SOS proof. Okay, So even though, we only proved the inequality, we ended up with a conclusion, a stronger conclusion, that in fact, there is a degree 2t sum of squares proof of that inequality. Okay, good. Some vigorous hand waving. So this F, first of all, I should not even say ideal because there are inequalities. But this F basically, is the kind of function that we wrote down the last time. It's a multiple of, um, um, polynomial inequalities that appear in our constraints, as long as they are low degree. Okay, so it's a function of the following kind. So, here you're assuming that, let's say f AW is, fi W is 0 for, 1 less I less than something. Then f, is a function of the form which is rendered non-negative by, by means of being a polynomial combination of the constraints here. So PS is sum of squares, and degree of each PS times product Fi is at most 2t. Okay, so formally, formally we never tracked this F. We never, like, even though we can extract an explicit expression like this from the proof we just did, we never quite did it. But, if we verify that each step actually has a low degree sum of squares proof, then you can, like, collect those terms together and at the end derive an identity of this sort, that you basically ended up proving an identity of the form that sum WCI square minus 1 minus delta is, some function which is a sum of squares polynomial in W, plus some function, which is, a non-negative, in fact, a SoS combination of the inequalities that appear in AW. Okay. So that was, I guess, what I was saying earlier, but that's just a restatement of the fact that, the proof we did, in fact, yields a degree 2t sum of squares proof. That's great. So now, we can go ahead and discuss algorithm, which we haven't done so far. Why should, this, what we did, be any, why should it be related at all to an algorithm? But it's not such a surprise that, to design an algorithm, we are going to compute a pseudo distribution that satisfies AW. Okay, so our algorithm will now, use the reasoning we did to somehow extract clusters from a pseudo distribution that satisfies, this inequality system AW. So, what have we done so far? Maybe, like, it's good to clarify what we have done so far. So far, we know that if W satisfies AW, then in fact, W is close to a true cluster. Right? That's what our soundness implies. So the natural algorithm here would be to just search for, W that satisfies AW, right? But usually we cannot quite do that. Solving polynomial inequalities is hard. So instead, our algorithm involves finding a pseudo distribution over W's that satisfy AW. Okay. Good. So imagine that this pseudo distribution. So first imagine. So for defining the algorithm, it's maybe good to imagine a situation where let's call this pseudo distribution D, because we already have used mu today. So first imagine that this pseudo distribution D happens to be an actual distribution. Okay. So now if D is an actual distribution that is supported on W's that satisfy, all the constraints in AW, then our soundness proof implies that, each W in the support of the distribution D must in fact be close to a true cluster. Right? So given such a distribution, which is supported on potential true solutions or approximate true solutions, how will you calculate one true solution? How can you calculate one true solution? if I gave you an actual distribution?
You can sample.
Right. So, you know, if indeed I had D, then I could sample. But you know, in our world, we actually don't get access to, you know, the distribution D. In fact, we don't even get a distribution D. But even if we had a distribution D, we don't get access to all of D, right? We only have low degree moments of D, right? We can only compute expectations of low degree polynomials, you know, on the distribution D. We can't quite sample from it because we don't know what happens to the distribution. We don't even know what expectations with respect to distribution are for higher degree polynomials, right? So in particular, like the distribution, the pseudo distribution we'll compute will be of degree, let's say 2t, which means that I'm only allowed to compute expectations of degree up to 2t polynomials. So notice that even if, so the point I'm making is that even if the pseudo distribution happened to be an actual distribution, it's somewhat non-trivial of a problem to get one solution out of it. Okay. And now, you know, so for that we will use you know, so maybe like we'll make one observation about it, and it will become clear how we can still do it. Okay. So here's the observation. Let mu be a pseudo distribution satisfying AW of degree bigger than 2t. Okay. Then oh no, I can't call it mu. Sorry about that. Okay, so if D is a pseudo distribution of degree at least 2t that satisfies AW, right? Then I claim that the pseudo expectation of this polynomial WCI square, which is really a degree 2 polynomial. So to compute it, I only need, you know, degree 2 moments of D is at least 1 minus delta. Okay, why is that? Well, you know, we proved that, you know, or at least we sketched that, you know, sum I equals k WCI square minus 1 minus delta is SoS of W plus some F, you know, which is in the, you know, this square SOS combinations of AW. So let's call it SOS combinations of AW, right? And so now, you know, let's and so all of these are like degree at most 2t polynomials. So in order to, you know, compute expectations of the right hand side, I can compute the expectations of the left hand side. Okay. And now, you know, simply conclude that because this is a degree at most 2t polynomial and because D is a degree 2t pseudo distribution, it must give a non-negative value to the first term. And because, you know, my pseudo distribution satisfies the non-negativity constraints that appear in A sub W, it must give a non-negative value to F. Okay. And so, you know, this is a simple proof that, you know, of the fact that, you know, if I gave a degree 2t proof of an inequality, then degree bigger than or equal to 2t pseudo distributions would in fact satisfy that inequality. Okay. Again, feel free to stop me because we're almost done. Okay, good. So with that observation, we are doing very good now. So let's understand, what our algorithm is going to be. So for that, let's examine, this inequality that we observed is going to be true. So we observe this inequality. This, also means, just like in the way we actually approach the proof, that the pseudo expectation of this, unequal cross terms is at most delta. Okay. So now, I want to use this statement to observe something about the matrix M, the second moments of W. Okay. So you remember what this matrix, you understand what this matrix is? The entries of this, so it's an n by n matrix. It's indexed by samples, basically, right? And the ijth entry is expectation with respect to D of Wi, Wj. Okay. And so what is this statement saying? So now, imagine that you basically look at the block. So, arrange this matrix so that, the true clusters appear as blocks. Okay. Just to look at how it looks like. Okay. Then, this quantity here is basically the sum of all the entries in off diagonal blocks. If the true clusters form, if you look at this as a, k by k block matrix, so look at it as a k by k block matrix with the true clusters as the blocks. So each of these blocks is like n by k, n over n by k by n by k. Then, what this statement says here is that the sum of the off diagonal blocks is at most delta. Okay. On the other hand, if you look at the sum of the diagonals, what should it be? The diagonals, is basically sum of Wi. And remember, sum of Wi equals n over k is a constraint. Right? So the sum of the diagonals equals n over k. Oh, and I guess, so this is delta times n square over k square. That's like, this is a normalized statement. There's a k over n that sits in here. So if I look at this matrix, whose entries are expectations of Wi, Wj, then, we are saying that the diagonals sum up to n over k, while the off diagonals contribute at most delta times n squared over k square. Okay, still with me? Good. So now, I somehow want to interpret this statement as saying that, that most of the mass in this matrix lives in the diagonal blocks, and that the off diagonal blocks contribute, a little, like something tiny to the mass. Okay. This is legit to do because, first of all, this matrix is non-negative. Can someone tell me why this matrix should have non-negative entries?
Because Wi, all the Wi's are positive or non-negative.
So we have Wi square equals Wi as a constraint, right? And we know that, the pseudo distribution satisfies this constraint. That means that, for the pseudo distribution, e twiddle Wi square should be equal to e twiddle Wi. Okay. Now squares must get a non-negative expectation. So this means that, e twiddle Wi's are all, bigger than or equal to 0. The same argument actually applies to Wi, Wj. No, because each entry is actually equal to an expectation of a square because of our constraints. And because, the distribution satisfies those constraints, it must be non-negative. Okay, so now what, so roughly what we've concluded is that the statement we proved implies that the off diagonal blocks contribute to something tiny, while the diagonal blocks, contribute some non-trivial, have some non-trivial mass. And so you can expect, some simple procedure that just, looks at a random row and reads off the large entries to be enough for rounding. like extracting two clusters. And in fact, that works. So I'm not going to do this in detail. I'm just gonna like write it down. The description of the algorithm. So find a pseudo distribution D satisfying AW of degree bigger than 2t. 2. Choose a random row of M. Take n over k largest entries in that row. And repeat. So this plan almost works, except there is one issue with it, which is the last thing I'll point out for today. Which is that all we know is that if we had an actual distribution, and actually we saw that our argument only uses this conclusion of the soundness, so really it also extends to pseudo distributions of degree at least 2t. We kind of know that if we had an actual distribution, it should be supported only on some things which are close to being the true clusters, right? But we don't quite have control on what distribution it is. It could be an arbitrary distribution which is supported on things close to true clusters. In particular, it could be just the distribution that outputs C1 all the time, or it could be the uniform distribution on C1, C2 up to CK. Right? So a priori, we don't have a way to even force D to have information about all clusters, right? Because if all the distribution did was return, the single cluster C sub 1, which is a valid solution, then we won't have any information about the cluster C2 to CK. Okay? So we need to force D to have information about all clusters. And the way to do it, at least one simple way to do it here, is to simply force that each individual Wi should be equal to 1 over k for all i's. Okay? So I don't just find any pseudo distribution. I also, find a pseudo distributions which satisfy that each individual Wi is 1 over k for all I. Now, if I add an extra condition like this, I have to check, one, whether I can do it efficiently, and two, if there is even a solution to this extra condition program, right? Can someone unmute themselves and tell me why both these things are actually legit? Like, the program is still feasible, as in I can still find a pseudo distribution which satisfies this extra condition. And two, this condition doesn't like, there's still an efficient algorithm which can handle this extra constraint. Okay, so the extra constraint part is
uniform distribution over actual clusters would work, right?
Perfect, exactly. The uniform distribution on actual clusters is a solution which satisfies each individual Wi equals 1 over k for every I, which means that this program is not bogus. There is a solution to it. Okay. And now, why doesn't adding this constraint hurt me in terms of efficiency of the algorithm? Why can I still solve it in polynomial time?
This is like a linear constraint on the entries of the moment matrix.
Yes, absolutely. So it's a linear constraint, and in general, in fact, I can add any convex function of the entries of the pseudo moment matrix, and I can solve I can solve the SOS program with that additional constraint thrown in. That won't really change anything in terms of efficiency of the algorithm. And so yes, so because this is just a linear constraint here, yes, it's it's still the same algorithmic statements for pseudo distributions applies. Like you can find pseudo distribution that satisfy this extra linear constraints in the same amount of time. Good. So that's basically the whole algorithm. Find a pseudo distribution, force it to give information about all clusters by forcing the means of variables to be 1 over k for every I, And now, just like use the conclusion of the soundness to infer that, the off diagonal blocks, when you look at the matrix as a k by k block matrix, add up to something very tiny, which means that if you do this simple rounding where you choose a random row and take the largest entries, 1 minus delta fraction of the entries would in fact come from, the true clusters. So the details of this argument, they're like pretty simple, but I won't do it today because I'm already out of time. But that's basically the whole 1D algorithm. Okay, so I've explained to you the whole 1D algorithm. I have not explained to you, so this completes So what I want to do is, like maybe take 2 or 3 minutes of your time to explain to you at least, the whole procedure works just the same. And part of it I have a reason to do the next time because of a different application. But I do want to tell you the test for higher dimensions before ending today. So I'll just take like 2 or 3 minutes extra of your time to tell you that. So, recall our test from before, okay? Our test for the case of 1D was to check if, C hat was of size exactly n over k, and 2, that if I look at the samples in C hat and, take the empirical deviation around its mean, then it is, whatever, tiny. Now in higher dimensions, I have to look for, some test that makes sense, when xi and mu are vectors, right? So what's the natural thing I can do? Can someone suggest to me what should I do here? What's the natural way to generalize this to higher dimensions? Okay, since it's like 6:50, let me, make a suggestion. So the 2 prime could be, so one is like obviously the same, there is nothing else to do there. 2 prime, one way to, incorporate vectors is to compute, L2 norms, right? I don't know what the threshold should be, but one way to generalize, this 1D test that we did is to just compute L2 norms. All right. This doesn't work. Okay. But in fact, it's nice because, and I'm just going to make this slightly cryptic comment, that if you look at this, result of Wimpala and Wang that we talked about at the beginning of the class, which got this k to the 1/4 result, even though the algorithm is not SOS, you can go back and try to, discover, every algorithm in some sense has to have certain kind of check for true solutions. Every algorithm must, implicitly come up with a way to distinguish true solutions from fake ones. So you can ask, what is this underlying property that, the algorithm of Wimpala and Wang checks? Turns out that they check something very similar to this. And so in particular, if you were to do this test, you would get stuck at d to the 1/4. You can change d to k by some, some simple trick, but basically, this k to the 1/4 that you saw in Wimpala and Wang comes from really using this as a test. Instead, what we will do is use 2 double prime, which is the following modification. So instead of testing the norm, we will look at moments of directional projections of these points. So we will take xi and mu hat and project them in some arbitrary direction v. So v is a vector in R to the d, and check if this is exactly the same value that we saw earlier. And this is legit true because, after I project to a single direction, I have a 1D function. And, one thing you can observe is that, if I started from a Gaussian distribution or actually even a sub-Gaussian distribution, the projections are also Gaussian. Okay, so in some sense, I have to check this condition, but I have to check this for every direction v. Okay. So now, there are concerns about how, I can even, I can even make these checks. There are like infinitely many of them. And eventually our checks translate into polynomial inequality constraints. So we seem to have ended up with a version which has infinitely many inequality constraints to check. All of that looks weird. But, next time when we meet, I'll tell you about a way to use sum of squares proofs to not just solve problems like this, but also to compress constraints like this. So we'll see a way in which we can use sum of squares proof in a different way in order to arrive at a compressed representation of this infinitely many sequence of polynomial inequalities, which is the program we eventually use in the higher dimensions. So this sounds more complicated than it is. It's actually much simpler, but this is something that we'll do the next time, and we'll do one more application of this idea that you can compress infinitely many inequalities into polynomially many inequalities by using sum of squares proofs. So next time we'll see succinct representations of polynomial inequalities, again using SoS proofs. And that's the essentially only hurdle in translating the 1D algorithm to higher D algorithm. The proof that we did, the soundness proof that it did for analyzing the test, essentially goes as is, with like one simple modification. And at the beginning of the next class, I'll do that for you before moving on to the succinct representation business. Good, but now you know enough about this result in sufficient level of detail, so I can stop.